Hello, I am wangzihan. Quick background, J-20 was developed to deliver a stealthy, long-range fighter for heavily defended airspace. In the early phases, propulsion was the hardest part. High-thrust engines were still maturing and not immediately available, while the program faced pressure to field capability on schedule. That mismatch created a classic systems engineering challenge: deliver mission outcomes under a tight power budget. Today, I'll show how we treat power like a fixed budget, save power, raise efficiency, and verify results with solid evidence. Next page. In the near term, we cannot swap to a stronger engine. Our power budget is tight. Without changing the engine, what can we do at the system level to recover capability? Success in plain words is three things: fly far enough, be detected later, and keep aircraft available. My goal is to connect these outcomes to specific design choices and test evidence. Next page. Here's the system boundary. The system includes the airframe, the air intake, the engine, the internal weapon bay, and the avionics. The actors are pilots, maintainers, command, and the developer team. The key interfaces are simple: air to intake, to engine, to thrust, airframe to weapon bay, avionics to missions. These are the places where improvements can multiply, or where changes can conflict. Next page. Now we move from expectations to measurable requirements. The top expectations are stealth, range, payload, agility, and availability. We make them measurable. To save power, we lower baseline drag. To expose less, we reduce external stores and carry more inside. To maintain faster, we bring mean time to repair down. Each expectation is linked to a design decision and a test item, so we always know what changed and how we will prove it. Next page, think in a causal chain. When power is limited, saving power matters more, just like running a family budget. We have three main paths. First, reduce drag so the air pulls less. Second, deliver smoother air to the engine so it wastes less power. Third, align the control strategy with the airframe so it does not fight the flow. Every change has trade-offs in space, maintainability, cost, and schedule. We name both benefits and trade-offs upfront. Next page. Option 1 is a shape that saves power. The body helps carry lift so the wings are not working alone, which means we need less push from the engine. We also smooth the outer flow so air slides past with less resistance, which lowers baseline drag and frees power for range or agility. Finally, we align the control strategy so handling stays natural and safety margins stay intact. Next page. Option 2 is to carry stores inside and feed the engine smoothly. Internal carriage makes it harder to detect and reduces drag by removing external hang-ons. A smoother intake gives the engine more stable air, wastes less power, and helps the engine hold thrust during demanding maneuvers. The trade-off is tighter internal space and sometimes harder maintenance, which we account for in verification and scheduling. Next page of changes are not instant, so we consider dynamics and delays. Picture a bathtub. The stock is the aircraft already in service. The flow is the upgrade rate. Delays stack up from design to test to scale up to fleet-wide rollout. We plan the cadence with small, regular upgrade packs aligned to maintenance windows. That way, we protect availability while improvements flow in. Next page. For verification, we use a plain English V model. On the left, we write needs, sketch solutions, and fix interfaces. On the right, we test small items first, such as an intake mockup or a bay door mechanism. Then we test the whole aircraft in flight and mission scenario, and finally, we do user acceptance. A traceability matrix links each need to specific test evidence and keeps us from chasing ideas that do not move mission metrics. Next page. Here are three measurable steps. First, a small drag reduction package with a target of baseline drag down by X%, proven by wind tunnel, CFD, and flight data. Second, pair the intake and engine testing with a target of better thrust hold during high G maneuvers, proven by bench and flight. Third, upgrades in cadence with quarterly release packs and KPIs of higher availability, lower mean time to repair, and lower defect rate. The main risks are tunnel vision on a single KPI, schedule slips, and mixed data definitions. We mitigate them with a balanced KPI set, milestone reviews, and one unified data dashboard. Thank you.